Welcome to this electronic devices and circuits lab. So today in this laboratory, we are going to perform one of the very important experiment which is about the Clipper circuits. So those who are studying the basic electronic subjects or electronic devices circuits or analog circuit subject, they may come across this particular circuit which is known as Clippers. So the other names of this Clipper circuit is slicers, voltage or current limiters, or amplitude selectors. So these are the different name of this particular Clipper circuits. So today we have to perform one experiment based on this particular Clipper. Okay. So first of all, we have to understand what is this Clipper circuit, what is its functionality, and how we can make a different kind of Clipper circuit, and the same we will be going to implement onto the MultiSim. So first you try to see what is this Clipper circuit. So basically this Clipper circuit is fabricated out of diode and resistor combination. Okay, so what are the two basic elements that need? One is diode and another should be one resistance. Okay, so by proper arrangement of these two components in the circuit, we can be able to make a different kind of Clipper circuit. So by definition, if you see what is the meaning of this Clipper circuit, the meaning of this Clipper circuit is that the circuit will be capable of clipping off a certain portion of a particular alternating signals. So what does it mean by clipping off a certain portion? Okay, so some portion of the input waveform is going to be clipped off without distorting the remaining part of the input waveform. So let's try to understand this very basic simple circuit that you already have seen. You might have seen this type of circuit earlier, which is nothing but your half wave rectifier circuit. Okay, so here you can see that we are having a diode in series, we are having a resistance. Okay, so let us suppose that if we connect a certain voltage at this particular terminal, okay, this is our anode terminal of the diode, and here we have the cathode terminal of the diode. So let us suppose we are connecting a certain voltage, and this voltage is nothing but is our square wave. So let us suppose that this diode is having its ideal nature. Okay, so if it is an ideal diode, then you must be aware that whenever this anode will be at the higher potential than the cathode, then this diode will be acting as a on circuit. Okay, so it will be acting like a on circuit, and this will be replaced by equivalent circuit, which is nothing but a short circuit. Okay, so at that time this diode will be in conducting stage. So whenever this this anode is in the lower potential than the cathode, that time this diode will become reverse bias and it will be in the off condition, and that time this diode has to be replaced by the open circuit conditions, right? So here you can see that if we are considering it to be an ideal diode, so whenever this potential that we have applied, because it is positive positive voltage, here you can see whose value is equals to V. If we are applying it, then this diode will become forward bias and it will get short circuited. And because of that, this voltage is going to be appear across this resistor. So here you can see that this positive voltage, okay, the positive part of this particular waveform is going to appear across this resistor. Okay, and that waveform will be look like something like this. Okay, it will look like something this type of waveform. Similarly, if you apply any other waveform, because we are talking about any alternating waveform, so if it is a triangular waveform, you can see here. Okay, so this is the positive part of the triangular wave. So whenever this voltage is having positive value, okay, that time this diode will be on, and then this voltage will be appear across this resistor, and we are going to get this particular positive portion of this particular input waveform. So here you can see what we are doing is we are actually clipping off the negative portion of our input waveform. Okay, so here you can see in the output, when we are taking the output across this resistor, we are actually getting the only positive part of the input waveform, and the negative part of the input waveform is actually being clipped off, and it is not appearing across this resistor because of this particular combination. Okay, so here again you can see actually, if you see in the circuit, this particular arm is called as the series arm, and this arm is actually called as the shunt arm. Okay, so based on this, there may be a chances that this diode may be connected in the series arm, or it may be connected in the shunt arm. Okay, so here in this case, because this diode is connected in the series arm, and because this circuitry is actually clipping off the negative part of our input voltage, therefore this type of clipper circuit is known as negative series clipper. So what is this series means? The diode is actually connected in the series arm, and this negative clipper means it is clipping the negative portion of our input waveform. So that's why the name is derived as negative series clipper. Similarly, there may be cases in which this diode will be connected in the shunt arm, and this resistor will be connected in the series arm. So here is the example. You can see that the diode is actually connected in the series shunt arm, and the resistance is connected in the series arm. So in this case, if you apply any input waveform, okay, any alternating waveform. So in this case, we are applying a sinusoidal wave here. You can see. So when we apply the sinusoidal waveform, and if you consider this diode to be an ideal diode, then you can understand if you take the like voltage across this diode, then you can find that whenever the voltage V is greater than 0 volt, that time this diode will be forward biased by the potential, and therefore it will be in the conducting stage. Why? Because this anode will be at more or higher potential than the cathode, and therefore it will be forward biased state, and it will be in the on state. So at that time, if you consider this diode to be an ideal diode, that time the potential drop across the diode will be 0. So here you can see that whenever it is input voltage which is greater than the 0, that time the output across this diode will be 0, and the a diode will be in the on state. Okay, so here you can see when we are getting this positive half of our input waveform, in that time the voltage across this diode V output is actually 0. Okay, because it is in the on state, and the voltage drop across the diode will be 0. Similarly, when we are getting this negative half of the input waveform, that time this diode will be in the reverse bias state, and it will be acting as an open circuit. Okay, so when you replace it by the open circuit, whatever be the potential that you have applied here, that will be appear across these two terminals. Okay, so whatever be the input waveform, the same waveform is going to be appear across these two terminals. Okay, so this is our waveform that we are going to get here. Okay, so you already aware of that. This is your output of your rectifier. Okay, generally we are connected half wave rectifier. So generally what we do is, we are in the case of half wave rectifier, this diode is actually connected in the series arm, and you are getting the positive half of the cycle. Okay, only positive half of the input waveform you are going to get, but here you are getting the negative half. So normally this type of clipper circuit, because it is clipping the positive portion, okay, of our input waveform, and therefore it is called as a positive clipper. Okay, and because this diode is connected in the shunt arm or parallel arm, you can say, so therefore its name is given as the positive shunt or parallel clipper. Okay, so basically based on the position of your diode in the circuit, whether it is connected in the series arm or shunt arm, okay, we can have a two different category of our clipper, which is known as the series clipper or shunt clipper. So what it does, positive clipper means it is clipping the positive part of the input waveform. And what does it mean by the negative clipper? It clips off some negative part of the input waveform. Okay, we have another class of our this clipper circuit. Okay, so here you can see that there may be a cases in which this circuit can also having a certain DC supply, okay, connected in series. Okay, so it may be connected anywhere in the circuit. So if we are having any DC supply connected in the circuit, in that time normally it is known as the biased clipper. Okay, so based on this key, whether this DC power supply which is being connected in the circuit, whether it is making this diode forward bias or reverse bias, based on that we can give a name to this particular clipper circuit. For example, here in this case, you can see, because this negative terminal of this particular DC power supply is connected to this anode terminal, And if you make it short, you will find that this positive is actually connected to the cathode terminal. And therefore, it is actually making it a reverse bias, okay? Making this diode as a reverse bias diode because of this polarity, okay? And therefore, because it is a negative clipper, we have already seen in the previous slide, it is a negative clipper. Okay, this circuit was a negative series clipper because this diode is connected in the series arm and it is clipping the negative part. So the name derived for this particular clipper is negative series clipper with negative bias. So why it is negative bias? Because this DC supply is actually making this diode reverse bias. Okay, and that's why its name is given as the negative bias. So if you change the polarity of this particular DC power supply, or if you change the direction of this diode, okay, and that time it will become if you change this direction, this will become positive bias, okay, direction of the diode, because that time this negative will be, this cathode will be connected to this negative terminal of the battery, and this anode will be connected to the positive terminal of the battery, okay. So that you remember. So whenever you have this type of circuitry, okay, of the clipper, you can also solve it by having while writing the Kirchhoff voltage law. Okay, so whenever you have this type of circuitry, you have to have you should know that whether this diode is ideal or if it is a practical diode. So in the case of ideal diode, you obviously know that whenever this diode is in the forward state, okay, this will be replaced by a short circuit and there will be no voltage drop across the this particular diode. In the case of diode is considered to be an ideal diode. But whenever it is a practical diode, then what we can do is we have to replace this diode whenever it is in the forward state, forward bias state, by its cut-in voltage, okay, or its thermal voltage, which is equals to 0.7 for in the case of silicon diode, and it is equals to 0.3 volt for your germanium diode. So based on that, you have to replace this diode with its equivalent voltage value. Okay, it's cut-in voltage value. So normally you can see this is the ideal diode characteristics that you may have come across sometimes while studying the diodes. Okay, so this is your equivalent, means it's VI characteristics for your ideal diode, and here we have the simplified model for our uh, practical diodes. Okay, so normally this is a simplified model in which we can replace the diode with its cut-in voltage in series with the ideal diode. Okay, so this way you can replace, and whenever the diode is in the forward bias, this will be replaced by short circuit. Whenever it is reverse bias, this will be replaced by open circuit, and this voltage has to be removed. Okay, that time it cannot be connected, because in the case of reverse bias, the diode is normally open circuited. Fine. We can also use the piecewise linear model. Okay, so like this, here you can see that we are having this voltage, and at the cut-in voltage, you can see that the voltage is actually not changing, but it is only current is changing. So voltage across the diode is not changing in this case in the simplified model. But normally in the case of piecewise linear model, you will find that there will be a little variation in the voltage across the diode will also change. And you will find that this characteristics will not directly go vertically up, but it will have a certain slope, okay? A certain slope that actually account for the resistance offered by the ideal by the diode, okay? So here you can see, if you take this consideration, okay, if it is considering to be an ideal diode, so normally whenever it is a forward bias, we have to find out at what voltage, okay, this will become short circuited. So let us suppose if it is in the forward bias state, then it has to be replaced with the, means the voltage drop across the diode will be 0 volt, and then it will be replaced by the short circuit, okay? Then you have to write the KVL expression, okay? Kirchhoff voltage law you have to write, and after writing that, you will be able to find out what will be the V output equation. So V output here in this case you are getting is V output equals to V input minus capital V. So this capital V is nothing but the bias of DC power supply voltage that we have applied. Okay, if you consider it to be an ideal diode, obviously you will be getting one more term. This VD will not be 0, but it will be something like 0.7 volt or 0.3 volt, depending on the type of material used for your making the diode. Okay, so that time you will be getting minus 0.7 over here. Okay, so this way we can also solve our circuit. These are the different circuits. Okay, so that you have to remember whatever I have explained you. So whenever we are getting like here we have this this is your negative clipper, negative series clipper that I have told you in the previous slide. So normally in the case of clippers, we need to know what is the transfer characteristics of this particular clip. So what does it mean by the transfer characteristics? So generally we have to, this transfer characteristics is nothing but it is the plot between the V input and V output. So here in onto this particular x-axis here we can see that we have actually taken the input voltage and here we are taking the output voltage. So here you can see in this case, if we are considering this diode to be practical diodes, so when this voltage we are increasing, okay, when the voltage is positive and we are increasing, then up to the cut-in voltage, there will be no significant current flowing through this circuit. Okay, so ideally what we can say that this output voltage up to 0.7 volt, okay, of the input signal, this output voltage will remain zero. So here you can see that when this voltage is positive, the input is positive, and we are reaching up to 0.7, there is no output. Okay, because there will be insignificant current flowing through this resistance, and therefore this output will be negligibly small, and therefore we are not getting any output. But once this crossing this 0.7 volt, okay, you know that the current in the diode is rising exponentially. Okay, so there will be a huge amount of current starts flowing, okay, after 0.7 volt, and you can find that this voltage drop across this resistance will be increasing linearly. Okay, so this is its curve. Okay, this will be going to be increasing linearly after that whenever this current is increasing, or whenever this voltage input voltage is greater than 0.7 volt. Similarly, whenever it is having a like negative cycle, this V input voltage will be less than 0 volt, and that time you can find that there will be no output across this resistor. Why? Because there will be no current flowing through this resistor, because this diode is normally in the off state, and in the off state this diode will be replaced by its open circuit, and therefore there will be no current, and hence we are not going to get any voltage drop across the resistor. Here you can find out, we have to make this table. Okay, so at V in less than 0.7 volt, V output will be equals to 0, and in that case this diode D1 will be in the off state. Okay, similarly when V in is greater than 0.7, this V output will be something equals to V input minus 0.7 volt. Okay, because here we have to write the KVL expression. So here we are going to get the voltage drop because the diode equals to 0.7 volt, and you then this voltage V output you can calculate, that will be equals to V in minus 0.7 volt. And in that case, this D1 will be in the on state. Okay, so here I have written like it is in the on state, and here this D1 will be in the off state. So again, you can see this waveform. Okay, so when we are applying any voltage, if it is a sinusoidal wave, okay, so as you know that sinusoidal wave, it will start increasing slowly. Okay, and it will first reach to this 0.7 volt. Okay, so this is the voltage amplitude that I have shown over here. Okay, so when it is reaching up to 0.7 volt, up to that there will be no current. Okay, no current flowing through this register, and therefore output will be remain 0. So here you can see that V output curve. So this is remains 0. There will be no significant output voltage you will find, and after that when it is going beyond 0.7 volt and positive, then that time this portion is going to appear across this resistor. Okay, so this will be the value. This will be the waveform at the output of our this clipper circuit. So again, when it is less than 0.7 volt, okay, once this voltage will become less than 0.7 volt, that time again this output will become 0, and its complete negative cycle will be clipped off. Okay, so anything voltage which is less than 0.7 volt, that is not going to appear across this resistor, and we are going to get this type of waveform. And here you can see that this maximum voltage that we are going to get is Vm minus 0.7. Similarly, again, you can do the analysis, similar analysis you can also make for this type of circuit when we are having this shunt clipper. Okay, so here you can see that whenever this shunt clipper is in the forward state, okay, whenever it is in the forward state and voltage is like 0.7 and more, at that time, you know that the voltage across the diode will remain constant and it is equal to 0.7. So here you can see that when this input voltage is greater than 0.7 volt, okay, at that time, this output voltage, because we are taking it across the diode, okay, that will remain 0.7 volt, okay, it won't change. Practically, you may find a little bit variation in this voltage, okay. Here I have just drawn an ideal picture, but practically you may find a little bit variation in the voltage, but that variation will be very small, fine. And whenever this voltage is less than 0.7 volt, and that time you know that because there will be no current through this diode, because diode will be in the off state, and therefore whatever be the input voltage, that voltage is going to appear across this open circuit terminal, okay. And therefore we have just this line, okay. So whatever be the input, okay, the same output we are going to get across this particular terminal, because it is having a slope equals to 1, okay. That slope will be equals to 1 and we are going to get the same output. So here you can see if we apply this type of input waveform, okay, okay, you can see that whenever it is a positive voltage, okay, here you can see when it is greater than 0.7, okay, this time, okay, 0.7, whenever it is greater than 0.7, that time you can see this output voltage is clipped off, okay, it is remain at 0.7 volt, okay. And whenever it is less than 0.7 volt, this portion is going to be up, right. So we are going to get this type of waveform. Here it will be clipped off, and then again we are going to get this portion. Hopefully you must be able to follow, okay. And similarly you can do this analysis. It will be very simple to understand when this diode D1 will be on and it will be off. It is important to do this analysis, okay. This mental picture should be very clear, then only you will be able to understand. Here you can see another circuit. If we are having this diode, this biasing, okay, if we are having some DC power supply connected in this series arm, then again we have to do the analysis at what time it is going to be forward bias and what time it is going to be reverse bias, okay. So here you can see this voltage when we have applied, okay. If you see, this is your positive terminal, so this is actually connected positive terminal here, and it is negative terminal is this side, okay. So initially when we did not have this particular voltage, if you remember in this previous picture, okay, you can see that we had this potential is up to 0.7. And now because we are actually, when it is forward bias, this will be positive and this will be negative. The voltage drop will be like this, okay, because the current will be flowing like this, okay, in the clockwise direction, and this will be a positive terminal and this will be a negative terminal. So this is positive and this will be negative. So if you do this analysis, okay, positive and negative, that time you will find that because this is positive negative and this is again positive negative, you will find that this voltage drop is going to be added. Okay, so if it is 0.7, then it will be added with the VB and it will become VB plus 0.7. The meaning is that the potential up to VB plus 0.7, okay. After this VB plus 0.7, this diode is going to start conducting, okay. It is going to start conducting, and that time this potential will become constant, okay. So after beyond VB plus 0.7 volt, this diode will start conducting, and after that, because it will be in the on state, okay, this voltage will remain 0.7, and therefore whenever it is greater than this VB plus 0.7 volt, whatever be the input value, if it is greater than this value, the output will remain at this VB plus 0.7. It will not increase further, okay. But below this VB plus 0.7 volt, as we can see that this diode will be in the off state, okay. This diode D1 will be in the off state. Why it will be in the off state? Because this DC power supply is making this diode reverse bias, okay. It is a negatively biased shunt clipper circuit, okay, and therefore it will be remain in the reverse bias state, and again this transfer characteristics will be something like this. Okay, it will having a slope equals to 1. And if you apply any sinusoidal wave like this, you can understand that up to this portion, it will be passing because it is having the same slope equals to 1. And then after this dotted line, it will be clipped off. Okay, so this portion is actually being clipped off, and then again, we are going to get this negative portion. Okay, again, you can do this analysis. You will find this these values. V in will be less than VV plus 0.7. Then V output will be equals to V input, and D1 will be in the off state. Similarly, when V in greater than VV plus 0.7, then this V output will be equals to VV plus 0.7, and D1 equals to in the on state. A similar analysis again you can make for a dual clipper. Okay, here what does it mean by the dual clipper? Because in the shunt arm we are having the two different diodes. Okay, and it is connected in the opposite direction. Okay, so when it is in the opposite direction, you can see that this diode is going to this diode D1 is actually going to clip a certain portion, and this diode D2 is going to clip a certain portion. So if you remember this diode D1, okay, this diode D1 is going to clip the positive portion, okay, and this diode D2 is going to clip the negative portion. So this will be the characteristics, okay, transfer characteristics. Here you can see that whenever it is greater than 0.7 volt, this diode D1 will be in the forward bias state and it will be in the on state, and this voltage remains 0.7. Okay, it is not going beyond 0.7. Similarly, when this diode, when we are applying a negative cycle of this V input waveform, that time this diode D2 will be in the forward state whenever it is greater than or you can say less than minus 0.7 volt. Okay, so again, it will be clipping this negative portion. So the output that you are going to get is this type of output you are expecting. Okay, both positive side and negative side is going to be clipped off. And because we are clipping both the cycles, okay, a certain amount of or certain portion of the both positive and negative cycles, therefore this clipper is known as dual clip. Okay, here you can see, you will find in the books that different type of clipper circuit you will find in the books, like positive clipper, okay, bias series clipper, okay, negative clippers, okay, biased negative clippers, okay, biased series negative clippers. So these are the different outputs that you can easily verify, and the same we have to implement onto the multisim. Okay, so we are going to implement the same thing onto the multisim. Okay, so these are the circuits that you can implement onto the multisim. Here I will just try to give a simple explanation about this circuit. Whenever we are having this type of series clipper circuit and we are having this DC power supply connected in the series arm, we have to actually do the analysis based on this. Okay, so because if you see this portion, okay, only this portion, if you see, these are the simply your clipper circuit. Okay, and here we have connected the DC power supply. So first of all, you have to make the analysis that whether this DC power supply that you have connected is actually shifting the your input waveform in the upward direction or in the downward direction. Okay, because it is going to give you certain DC component. Okay, it is going to add a certain DC component. For example, if you see in this case, okay, let us say in the bottom case. Okay, so because if in this case, if you see, if you are adding any DC supply with this polarity, okay, so whenever you are applying a particular voltage, like any waveform at this condition, and if you apply the KVL, okay, you will find that this is positive, this is negative, again this is positive, this is negative and positive. So it means that these two voltages are going to be added. Okay, and because it is going to be added a DC supply, you are adding to this particular AC supply. Okay, and therefore what generally happens is, if this is your waveform, okay, if initial waveform that you have applied at this terminal is this, okay, then what will be the effective voltage which is applying across this circuit, okay, across this diode and resistor network. Okay, so that will be a shifted version of this input waveform. Okay, whenever it is having this polarity and we are adding the DC supply, so this will be the shifted version. So this is the effective input waveform along with the DC that we are actually applying across this diode and resistor network. Okay, And therefore, based on this waveform, we have to decide what portion is going to be passed or which what portion is going to be clipped off. Okay, so simply here you can see, because it is this is a positive clipper, okay, because this circuit is a positive clipper, positive series clipper with a bias, okay. So therefore, what you can see is, because this will be the effective voltage, okay, you can see that this positive portion is going to be clipped off, okay, this all positive portion is going to be clipped off. Here you can see this is our ground level, okay, this is our initial ground level, okay, and this is our input waveform that we have applied. But because of this DC power supply, this is appear across this diode registered network like this, okay, this is the effective voltage or waveform that is going to be appeared across this network. And therefore, you can see that this is the positive portion of your input waveform. This is the entire positive portion. Okay, these are all entire positive portion. So this portion is going to be clipped off. Sorry, this portion is going to be clipped off of all the positive portion. Only this portion is going to be appear. So here you can see that this is the portion which is going to be appear. Okay. A similar analysis you can do for all other circuits. Okay, it is very simple to do. And these are the other circuits, okay, simple parallel clipper circuits, and these are the certain biased parallel clipper circuit. So now I am just moving on to the MultiSim software, okay, to perform the same experiment, okay. So how to perform this circuit? So let us suppose if we are having this small circuitry, okay, this is your negative series clipper. So first of all, you have to bring all these components, okay. So this is our waveform generator, which is function generator, and here we have the oscilloscope. Okay, you have to bring the diode and one resistor. Okay, you can take resistance value equals to 1 kilo ohm. It is sufficient to perform this, but you have to select the waveform according to your need. Okay, so here I have selected this waveform to be sinusoidal, and I have taken the frequency equals to 100 hertz. Okay, this peak amplitude I have taken 1 volt V peak. Okay, so the peak to peak value of the input signal will be equals to 2 volt, because this represents the V maximum value, right? So if you now make this circuit, make the proper connection the way I have done in this case, okay, if you execute the circuit, okay, you can observe the waveform in this particular oscilloscope. So here you can see this oscilloscope, okay, and you can see this variation in the output, fine. So you can stop it, and then you can see this waveform. You can just do the analysis, okay. So here you can see that this white colored signal is nothing but your input waveform, and this red one is your output waveform across this register. So here, because the sensitivity of the two channels are different, the output is connected to your channel B. So I'm just making the sensitivity, both sensitivity equals to 500 millivolt. So now here you can observe this output. Okay. So here you can see that there is a small lag. Okay. As I said that because it is a practical diode. Okay. Until or unless this input waveform is greater than the cut-in voltage 0.7 volt, there will be no voltage will going to appear across the resistance, and therefore this type of waveform you are going to observe. Okay, you can also measure this height. Okay, what will be the amplitude of this output? Okay, so that you can also measure, because it is a practical consideration. We have to also consider there will be a little bit variation across the voltage across your diode. Okay, it will not remain constant like 0.7 or so. So whenever it is a practical diode, that will be a little bit variation. So that you can measure by bringing out this particular pointers. Okay, I have already explained number of times how to measure this voltage in my previous lectures. Okay, so that way you can do this measurement. Now, again, what we can do is you can bring this DC supply. Okay, so let me just bring this DC supply over here. Okay, I'm just making a connection over like this. Okay, now it become a like your biased clipper. Okay, so now it is a positively biased clipper. So what kind of waveform that we are going to observe is, here you can see the positively biased clipper. Okay, because it is a series clipper. Here you can see this is our series clipper. Okay, so this is your positively biased clipper. So we are supposed to get this type of waveform. Okay, it is going to clip off the negative portion, but now more portion is going to be appear across this register. and a little bit negative portion is going to be clipped off. So if you execute this circuit, we are going to get this type of waveform. Again, you can just stop it, and here you can see that this is the waveform that we are going to get. Okay, a little portion of the negative is actually going to be clipped off, so you can again change this value, okay, a little bit, so that you will be able to perfectly see these outputs. Okay, if you wish, you can just make a little bit changes in the voltage, and you can do the analysis, okay, at what voltage what value we are going to see. You are connecting it 1 volt, you will be able to see this waveform. Okay, so this is the waveform that you are going to see. You can see that this portion we are going to get. Okay, this is the input, this is the output waveform. The input that we have applied is this. Okay, because of this DC power supply, okay, this waveform is going to be upshifted. Okay, this is going to be, and therefore a little portion at this negative side is going to be clipped off. Okay, and this type of waveform we are going to observe. Similarly, if you just make it reverse, okay, if you want to make it reverse, either you can in this case, okay, in this case in the multisim we have this flexibility that I can make it negative, okay, just putting a negative sign. But normally when you are performing this experiment onto the breadboard, you always consider changing the polarity. Okay, you have to change the polarity, otherwise it won't change. Okay, that you have to remember. So now if you execute this, okay, again you will be able to see this output. What kind of output we are going to get is here you can see this voltage is completely gone off. Okay, nothing is appearing. Okay, so you have to it means that there is no such portion that is making this diode forward bias simply. Okay, there is no such portion which is actually making this diode forward bias. So what you can do is, because we already know that this is the input signal, okay, and now because we have added means we have subtracted this -1 volt to this particular signal, so this signal will come down and its tip will become 0 volt. Okay, so obviously this diode is never been going to become a forward bias, and therefore we are not going to get this any output. Okay, so what I can do is just to make a like just to reduce this value, okay, magnitude 0.5 volt, that may be sufficient to see certain output. Okay, so now if you execute this one, okay, okay, so now we are going to get this output. Okay, you can see a little portion of this positive half cycle is actually being. So this way we are going to get this output. Okay, so again you can make a comparison with this. Okay, like in this case, okay, this is the diode, and here we have changed the polarity of your uh, input bias. Okay, so I have changed the values. Okay, you have to change the polarity. Okay, but I have just changed these values. In the case of multisim, it is possible. Fine. Similarly, again you can see this series clipper. Okay, shunt clipper, sorry. So here you can see that this is our shunt clipper circuit. Okay, so I can just let me remove this one. Okay, and then again you can observe this output. So if you execute this circuit, okay, you can see this circuit output. Okay, so here you can see what kind of circuit we are having. Okay, yes, so this is your shunt clipper. Okay, we are having this shunt clipper, and here you can see this out. Okay, a certain portion of this output is going to be clipped off, okay, of the positive cycle. Fine. So why this portion is becoming means it is clipped off, because this diode is becoming forward bias. So when this diode will become forward bias, okay, that time this potential will be remain 0.7 volt. So that you can measure from here. Okay, certain voltage around 0.7 volt, and then a little bit variation in the voltage we are going to get. So this type of waveform you are going to see. So here you can see this shunt clipper. Okay, here we have this shunt clipper. So I have made this circuit. Fine. So this is your shunt clipper circuit. So this type of waveform you are going to observe. I think some output is not properly matching. You have to see what's the problem. In this case, okay, it is 0.7 volt. Fine, it is okay, it is the right output. Okay, because this is a practical diode. Okay, we are not having the this ideal diode, and therefore a certain portion which is around 0.7 volt is going to be appear, okay, and something more than 0.7 or around 0.7 or 0.5 volt is going to appear across the diode, and this type of output we are going to get. Again, if you add a certain DC power supply, if you add a DC component, okay, let us suppose if we are adding this DC power supply, okay, you can please do the analysis by writing the KVL expression, okay, and then you use the piecewise linear model or simplified model of the diode, okay, and replace it with its cut-in voltage whenever it is getting forward bias, and then try to identify at what percent is going to forward bias and at what percent is going to reverse bias, okay. So this way you can do the analysis, fine. So now if you see this waveform, okay, so let me stop it and then again execute this circuit. So if you do this, okay, you'll be getting this type of waveform, okay. So now you can see in this picture, okay, we have this waveform, okay. This is your shunt clipper, okay, with negative bias, fine. So here you can see this is our shunt clipper and this is the portion, okay. So you are going to get this portion, fine, only this portion you are going to appear, fine, and then the rest of the part is going to be clipped off. So here you can see this output again. This portion is actually appearing, okay, and rest of the part is actually being clipped off. So hopefully you must have understood something about this clipper. You try to make this all circuitries, whatever I have shown here, okay. In these slides, you can implement all these clipper circuits, okay, and you can observe the output using the MultiSim. The same thing you can also implement onto the breadboard. So if you find any difficulty in understanding this clipper circuit, you please feel free to drop me a message in the comment box, okay. And thank you for watching this video and try to implement the circuit onto MultiSim as well as onto the breadboard. So thank you for watching this video and stay connected with the channel for more updates. Thank you.